for being here. We're going to talk about Pinot. If you were, who was in, I gave a talk yesterday. Who was in that talk? Okay. All right. Most of you not. Good. Just barely mentioned Pinot. This talk is all about Pinot. And for it to make sense, I want to take you through a little bit of history. And I asked about yesterday because I talked about a little of that history yesterday. This is a slightly different lens on it, but Pinot's a new database. And as I like to say, it's a terrible idea to build a new database. In fact, the guy who's my boss, who was on the team at LinkedIn that originally built Pinot, he kind of bumped into this problem, and he was like, I don't want to, like he has a life, he has kids, and he doesn't want to build a database. That's a terrible life choice. And so I feel like anytime there's a new database, there better be a good reason. And I think that reason is best understood in terms of some history. So we're going to talk about that history, and then we're going to talk about the architecture of Pinot, why it's fast, and how it fits together with Kafka. And there's really an interesting story, I think, about its Kafka integration. So that's what the talk is about. We've got an hour, 58 minutes left. Let's go and talk about a little history. I have been more and more interested in this recently. In fact, we just did at StarTree, we just did a special podcast series that's going to be finishing up next week called Keyboard and Quill. And it was like a technology history over time, starting in prehistory with like cave paintings and getting through printing and agriculture, writing, printing, the machine power, telecommunications, computing, and ending with Pinot. It was kind of have to be on message at some point. I've been more and more interested in history recently. So let's just start not with cave paintings. That would take a while. I'm actually writing a talk that kind of goes there, maybe next year. This is an IBM 1401 mainframe. It was not the first commercial mainframe, but one of the first that really achieved volume production, that there were many of them made. In fact, actually, let me, if you don't mind, there's something I forgot to do here. We do not want that. We want that. There you go. This was, and I mentioned I moved from Colorado to California. That's like about a 2-hour flight or a 20-some-hour drive. In Mountain View, where I live, 10 minutes from my house, there's a place called the Computer History Museum. I love that place. I have been known to spontaneously cry a little bit at certain parts of it. They just touch me, things from my childhood. Anyway, they have 2 of these that they've restored, and they actually work. You can go there on Saturday morning, and there's demo, and there's guys there who are not young people who were working on these when they were new, current technology. 5 years from now, that last part might not be true. We're kind of getting to the end of that. Anyway, it's amazing, okay? This machine and mainframes of its day, we're talking late 50s, early 60s, were batch analytics machines. That's what they did. You had a big pile of literal punch cards that you fed into the machine. You loaded the code on punch cards, and then you loaded the data on punch cards, and it would do things and print out on this big noisy printer that's just beautiful to see. Data ingestion was terrible then too, because the punch cards would fold and jam, and ingestion has always been bad. There's nothing we can do. Anyway, we got started there, and batch analytics was the thing. That's what we did. There was no idea of a transactional database. That was a foreign concept until terminals came along. And terminals came along a few years later. They became, like in the mid-60s, sort of a beginning to be a commonplace thing. Computers are fast enough now that you can actually hook something up and type and have a user interface that's not just dump cards in. And so you could engage in transactional things. And when things change out in the world, you can do stuff on the computer that causes those transactions to be recorded in some database here. State of the world changes, state of the database changes. That was a new thing. That came after batch analytics. But now there's both of these functions. You've got, we didn't say OLTP and OLAP at the time, but they began to be a thing. But since it was all kind of in one piece of code, reporting was just a feature of that software. You didn't have a data warehouse, or the kind of mess we live with these days wasn't a thing. It was just, here's a database, and we'll run reports on that database, okay? And they print it out on paper that looks like this. They actually, if you go to the Computer History Museum, you do this demo with the 1401, you can type in your name on a punch card on this thing that's actually punching holes in this character encoding, like who knows what it is. And they'll print out your name on a piece of green bar like this. It's fun. But that was what was going on then. Well, then what happened? You had the mainframe, it was successful. People started to make cheaper versions of the mainframe that we called mini computers, architecturally the same, but scaled down and lower cost. And there's this trend, which hasn't stopped yet, of computing getting cheaper and more accessible to more and more kinds of businesses. In the early days of the mainframe, you had to be a government, an airline, a bank, a public utility, something just of a massive scale to be able to afford computing and to be able to afford analytics. Well, get into the late 1970s, really early 1980s, and this other thing happens. You've got now PCs happening. Computers are cheap enough and fast enough that all of the storage and I/O and compute that you need to actually do interesting business things, like, say, spreadsheets and word processing, that now fits on a desktop, which is revolutionary. And people are, rather than everything being in a central place, software is running on everybody's desk. This was a revolution in software architecture, and it has a name. That name is client-server. And writers at the time, in the 1980s, I was nerdy teenage boy reading magazines like Byte magazine. If you don't know what that is, Google it, go look in the archives and just weep. It's beautiful. The covers in the 80s, there was this guy who painted them. Just check it out. Anyway, writers were talking about client-server like it was going to usher in a golden age. I mean, this was a new utopia. It was weird, right? Like, this is a software architecture. Relax. So people were crazy then, too, in terms of technology trends. But it really was a big change. And it broke the way analytics happened. Because where's the data now? Well, maybe on the disk inside the computer, maybe on a server in a closet just for the department. So instead of one big database that's centrally managed, and there's kind of priests that guard access to it, now everybody's kind of got their own little database in a closet, and data's everywhere. And how are decision makers supposed to have a view of everything in the whole business? Well, this led to the creation of the data warehouse. Now, that history is a little more complex than that. And in fact, that podcast, I'm not just here to plug a podcast, but if you look up Keyboard and Quill, there's an episode where we talk about the evolution of the data warehouse. And I interviewed Bill Inman, the guy who invented the data warehouse. So he tells a slightly more nuanced story. But basically, once you've got all the data scattered everywhere, you can't just go run a report on that. You have to get it into one place. And so this led to data warehousing, where there was this new process where at night we'd go read the transactional data from all the departmental databases, bring all that together, reformat it into some new, carefully designed, structured way, and put it into a single database for reporting. It was revolutionary. And it really was. It was a good idea. This is old-fashioned now, but in the 90s, it was critical technology. Then what happened? Well, the web. Not too many years after data warehousing started to be a thing, client-server is just getting its legs under it and starting to work, and, well, the web happens. And the people who are building web applications in, say, 1995, well, these are the young, cool revolutionaries who had just adopted client-server. They're like, mainframes are stupid. We have this new way of doing things. And they just picked up that whole tool set and built the web with the client-server architecture. Why would you do otherwise, right? It was fine. If you think back, if you've been around, you think back to, like, kind of the canonical J2EE thing where you'd have the data tier and the business tier and the presentation tier. Well, that's just client server, except with user interface that sucks, which was the early browser. So the web happened, and like nobody noticed. We were still doing client server, still doing data warehousing until the web really started to get some traction, especially when mobile devices hit. All right, as soon as mobile devices land, then everybody's life is going through a mobile device. There's too much data for client server to work, for the conventional data warehouse to work. We get this, I hope it was obvious, big data. The elephant that looks like it's made out of data. You have to spend a long time with the AI to get there's a lot of mistakes along the way here. But anyway, that big data happened, and that was really taking that idea of the data warehouse, where you get all the data from over there and you put it here, and just doing that in a bigger way, right? It was a more scalable tool set, a little more complex than that, but that happened. What's going on with application architecture around this same time? We're starting, we don't say client server anymore. What do we say? We start to use a dirty word. The monolith. The monolith is bad. We have to get rid of monoliths. That's just big, ugly client server, okay? And for good reason, we started to say that that paradigm was breaking down. Finally, the web was causing that to not work so well anymore. We started to write microservices, and it was ugly for a long time. That was a great idea and a lot of really bad implementations, in my opinion, until Kafka came along and we realized, all right, if we have these things sending each other events, these little services communicating through events, that seems to work pretty well. And it seems like we're starting to make those systems work. So this is all the history that leads up to Pinot, a third of the talk, but I like this stuff. So now we're in this place where the log, the Kafka topic, is increasingly, that's like the controlling abstraction underneath the systems we build. We're building services on top of logs. In the old days, and by that I mean like 5 years ago, the world was a database with a program around it. That's client server, that's monolith, that's whatever you want to call it. And we all kind of knew how to do that, and that was easy and kind of got good at it. Now it's a bunch of services talking through Kafka topics. This is the second, in the way I'm telling this story, if you just take my version of events here. You had the mainframe, it worked, they got cheaper, smaller, more people bought them. Then you had PCs, which instituted the world of client server. That was ugly at first. We got better at it, more products, solved had a new application architecture. That was really the first new mainframes from the 50s to the 80s. That was the way software got built. Now with PCs, oh, okay, this is different. We're going to put our data there. We're going to have clients here. This is a new architecture, new way of doing things. And it broke the way we did analytics, which led to the data warehouse. Now, for only the second time in the history of computing, we have another major new architectural paradigm. And I understand that that's a little bit of a simplification, but in this simple account, I think it's a good way to look at things. Now, event-driven architecture is pushing client server out of the way. I think there are people who are just learning how to eat food right now, very small people who are not very good at anything because they're babies. In 20, 30 years, they will be people who are writing software with the same event-driven paradigm that we're building now. Maybe by then it'll be old, and there'll be some new thing that you and I can't imagine that'll be pushing it out of the way. But I think it's that kind of thing. And just like client server caused the data warehouse to exist, event-driven architecture is causing a new way of thinking about analytics. That just requires a slightly different tool set. And that's what Pinot is. There you go. Let's talk about its architecture. See, like I said, if I'm going to get up here and I'm going to say, hey, database, and you should know about it, anytime anybody says that, they really need to have a good reason. And so I spend the time on the history because I think that's where we are in the development of our discipline right now. I think it really does matter, and we really actually do need this thing. So let's check it out. All right. Pinot's a database. There's not much to say about the data model. You put data, where do you put data? You put it in tables. Back in the NoSQL days, everybody's like, no, wait, the data model should be this other thing. And I mean, some of those worked, right? But for the most, tables are nice. And it took a long time. in the history of database development to get to that idea. It's not as obvious, and it's just a really good idea. So Pinot uses tables, rows, they have columns, the columns have names, the columns have data types. The only really different thing is you query them with SQL, but there isn't a create table statement. You write JSON specification files. Because create table, there's enough that you need to kind of say in Pinot that it would be one of those things where it's create table, blah, schema with options. You know how the vendor extensions, they get a little silly. You have those key value pairs. We're just like, you know what, screw it, it's JSON, done. So you define a schema file and a table config file, and there you go. Tables are split up. This is a radically scalable database. Tables are split up into segments. Those are units of physical storage. So you could think of a segment as a file or maybe a directory with files in it. And these are, when we're ingesting from a static data source, these are created during that ingestion process. We could also ingest from a streaming data source, and they could be created during streaming ingestion. And once a segment is written, it doesn't change. That's a glorious thing. It's an analytics database, so it kind of expects that things don't change. Asterisk, right? Sometimes they change. So we probably won't go over this in detail today. I'll point you to a website where you can get more information, but Pinot has support for upserts, which is not exactly unique in the space of real-time analytics databases, but it's got a very clean implementation. Upserts are efficient and work well. So can things change? Of course they can, but fundamentally segments are immutable. Yeah, so visually you have a table. It's made up of segments, and they look like that. Now, Pinot is optimized to be a database used for analytics, and that's an OLAP database. And so in a transactional database, generally what you want to be very good at is creating, reading, updating, deleting a thing, one thing that you have a predicate that is highly selective, and there's one entity, and you usually want to like get that whole entity out or put that whole entity in, maybe update a piece of that entity, but it's usually the whole entity that you care about. In analytics queries, you usually don't select star from table where ID equals. That's just not what you do. You usually select, average of a field from group by, or, where such and such, group by such and such. So you're looking at lots of records, in particular, a single measurement. You're usually looking at a metric of some kind, running some reducing function over that metric. So transactional databases want this thing, analytics databases want lots of things. As a result, segments are columnar. So I'll give you a visual to make sure that I'm clear on what that means, but the storage format is column-oriented, which is what you do if you're an analytics database. So if you had this data, this is a click somewhere, and that's a fine thing to do with a database like Pinot. Pinot, by the way, I should give you the origin story. It started at LinkedIn. The team that built Kafka started that like around 2010, and that took over LinkedIn's internal architecture and its data pipelines, and they're starting to build microservices on Kafka, very early adopters, because that's where Kafka was built. And an adjacent team had a problem to solve where they wanted to deliver basically the results of OLAP queries in real time to users on page load, right? So you've got, 50 milliseconds, 40 milliseconds, it's got to happen quickly. Traditionally, if you wanted to do that kind of thing, you'd have to pre-compute all that stuff and stick it in a key value store so that you could retrieve it fast enough. That's okay if you've got single dimensional queries, things don't change all that often, you don't worry about data being fresh. It stops being fun very quickly. So they then built a database to do that. And that's where Pinot came from. So clicks, user events, things like that, that's a use case. For whatever reason, meal delivery globally, like every global meal delivery service, I'm pretty sure that's literally true, has adopted Pinot, and a lot of them are even Startree customers. We want to feed the hungry. What can I say? there's a lot of meal delivery here. Anyway, clicks, fine. This is a fine kind of data. And if you look at the fields here, IP, user ID, whatever they are, the way a segment is physically constructed is all of the column values for each field are put together. In case you want to get to the point where you're scanning all of those in a segment, you could do that efficiently, because you very rarely want to go and get each value of each column and return the whole entity. You are more likely to say, scan over the bytes column in the segment. And so you want that stuff to be stored contiguously, so you've got nice sequential access to that stuff and faster reads. So that segment, if you looked at it close up, it would look like this, and you would have individual numbers pertaining to each row that you stored it for. So you break the row apart into segments and store them like that. So you got lots of segments. They all look a little bit different, but they're kind of basically the same thing. And those, we'll just give them numbers, and we'll put them on a machine, in terms of physical architecture here, called a server. As we know, naming things is hard, apparently very hard, because, aren't they all kind of servers, really? But that's what they're called, all right? Servers are, in a real sense, the true heroes of Pinot in terms of the physical architecture. It's where data is stored. It's where most of the compute happens for, when processing queries, that happens at the server level. And we can have many of them. There can be even hundreds of servers, millions of segments. All these things scale a lot. There's another machine called a broker. Is the broker also, is it not itself a server? Again, let's just go, let the names be the names. We've got servers, we've got brokers. Brokers can also scale, and they kind of serve as the proxies that clients talk to. So a query comes in, brokers are keepers of all of the cluster metadata. What are the tables? What segments are they composed of? What servers are there? What segments are stored on what servers? How are replicas allocated? These are all things that brokers need to know. That's all important. There's a Pinot, a real deep dive topic that's, honestly, it's worth its own hour-long talk, called query routing, that deals with how the broker intelligently uses that metadata to do, well, what I'm about to show you. A query comes in, and the broker intelligently uses the metadata, looks at the query, looks at what it knows about the segments, and says, you know what, I need segments 2 and 8, just based on what's in the where clause, what I know about time, any other clues I've got to go with. Maybe there's some Kafka partition things I know that I'll try to use. I need segments 2 and 8, so I'm going to talk to those 2 servers, distribute the query to those, or scatter the query to those. Those servers do I/O on the segment file, and sorting, grouping, aggregating, whatever that compute, and potentially more sorting, whatever computation the query needs, and they return a partial result for the segments they were responsible for. And the broker, like I said, query routing is difficult because on the one hand, you want to spread that out to as many servers as possible, right, to parallelize the work. On the other hand, spreading it out too far increases tail latency because that's more VMs. This is all written in Java. That's more VMs that might have a garbage collection incident happen. So it's like this dance where, as you look at the release notes in Pinot, optimizations and query routing is just an ongoing area of refinement as Pinot gets even faster. So it's a cool thing worth looking into in the docs. Anyway, you scatter the things, and sorry, skipped ahead. The servers return results back up to the brokers, and they join them into one result set and return that to the client. Now, before I move on to the controller and Zookeeper, this architecture here, because this is the simple introduction, and there's a lot to cover. This is the single stage query engine, which is historically the only engine in Pinot. As of about a year ago, 9 months ago, there's been the multi-stage query engine, where in that case, if you're using the multi-stage query engine, the broker comes up with this complete plan and says, okay, you 5 servers, you've got the raw data. I'm going to give you little parts of the query that I've broken down. You do those, and then I want you to route your intermediate data set to this other tier of servers. There's a shuffle operation going on there to try to get the right keys onto the right servers so they're local. Maybe like if you have a join or something like that to do. And these are large result sets. So the multi-tier engine can have those multiple stages to do things like joins, window functions. In the future, it'll do nested queries. So it's kind of the architecture for more complex things. It's obviously going to be slower to do it that way than the single tier. So it's perfectly fine to use the single tier if that gets the job done. And a lot of analytics queries, the bread and butter analytics query is filter, group, aggregate, maybe order, right? There's a lot of work that gets done just there. So joins are a thing, and we might want to be able to join, but that's getting outside of the core of what analytics usually does. All right, the controller, its job is, there's an API endpoint to manage ingestion, metadata changes like altering a schema, creating a table, and it pushes metadata to the servers. So anytime, to the brokers. If a server goes away, if a new segment is loaded and replicated places, that's a metadata change the controller has to tell the brokers because the brokers need to know that. Zookeeper off to the side, chilling as it always does. Just doing its job, getting complained about. That's all Zookeeper does. It sits there and it works and people hate on it to get more love. Finally, because all of these immutable segments are lying around, we all know full well they're going to have to change sometimes. You know, we have to go scrub for people who have deleted their accounts or do some kind of cleanup, or we say, oh no, this data got ingested and it shouldn't have been, or there's a schema migration, we have to do this thing. So the minions are, minion workers are another class of servers, a component off to the side here that are doing, they're the built-in distributed computation framework. So you can submit to the controller using an API, here's a minion job, jar, right? There's a very simple API, you implement that, you've got your minion task, and the controller will then distribute that to minion workers, which can then go, can't modify segments, but you can read segments, create new segments, load the new ones, drop the old ones, etc. By the way, batch data ingestion also happens, by default, typically happens on minions. So minions are often, when people talk about Pinot, and even in the documentation right now, and this is a thing we're working on, they don't really get a lot of honor, the honor they deserve. They're very important. They're a very important part of the system, critical for ingest and lots of maintenance tasks. There you go. That's it. That's the physical architecture, servers, brokers, minions, controllers, Zookeeper, nothing else you need to know about how it's put together. And like I said, you can do this in Docker on your laptop and just have one of each and play, and it works great. You can do this with thousands of nodes between brokers and servers and radical scale and everywhere in between. Wouldn't be a database if we didn't have indexes. This is kind of a place where Pinot shines. It's got a rich set of indexes, and internally, everything is pluggable. It's just got this very pluggable architecture, including for indexes. So if you wanted to write a new index, if these didn't do what you wanted and you wanted a new one, then you could write a new one. You don't even have to rebuild Pinot itself. You just have this jar and some config, and you can make a new index if you want. So again, I feel like everybody needs a hobby, right? But you might have a use case where you need that. Let's just go through this. I'm going to skip forward index and go straight to the inverted index. So the inverted index, backing up a step, I need to introduce a term. When you ingest or define a schema in Pinot, you don't need to define a primary key. If you do define a primary key, that's your primary key in terms of your data model. I mentioned upserts. If you've got some data source where entities are evolving and you're ingesting those. Upserts rely on there being a primary key. That stands to reason. The indexes don't think, because the primary key is optional, they don't think in terms of the primary key. They use a term document ID. And so as a row is ingested, that is a document. It has a unique identifier, a number. And so indexes deal in document IDs. Fundamentally, the inverted index is a way of saying for a given column, here's a value that column might have. Which document IDs have that value? So what are the rows where location equals Littleton? Would be a way of doing that. In other words, if we have this very simple table, these few cities here, those doc IDs, the index is going to contain a list of locations and then a collection of document IDs. And so for lower cardinality dimension columns that are string valued, this is a great way to go. What if you have something that is a number, though, and not some relatively low cardinality string? It could be an integer, it could be a real number, but it's an actual measurement out in the world, and maybe no two measurements are the same, right? Maybe they're all, like the cardinality is literally the row count. You might still want to be able to do interesting queries there. That's what you do with, use the range index for that. So again, it's mapping a value to a list of document IDs, but since it's a high cardinality thing, you just have to bin the values up. So it'll say, okay, we'll make, say, 10 of those bins or 100 of those, whatever that is, it'll figure that out, and it'll give a range of those values. And so you look for, and then effectively builds an inverted index based on that now low cardinality set of ranges. So if the value falls within that range, you get your list of document IDs out. There are two kinds of text indexes. Originally, Pinot had basically embedded Lucene, which is just, that's the way you do it. It's an Apache project. Got to be friends. We all love Lucene. And that remains and is the higher powered, lower performing text index. So if you need features that index gives you, it's the one you want to use. The native text index has a subset of those features, but is faster in performance and I think also in space that it takes up on disk. Don't quote me on that. But there are two of these now, and you just get to be smart about what you want to do. Basically, the rule of thumb you want to follow is use the native text index if it does what you want, and if you need to go to Lucene, go to Lucene. But this is for unstructured text, where I've got a column that's a description or some big blob of something, and I want to do text searches within that. Now, the JSON index. Let's think carefully about this. A lot of the data you might ingest into Pinot might start life as JSON, right? That makes sense. So why is there a JSON index? Well, imagine, I mean, you're going to take the JSON input and map fields to columns, and so it's not going to stay JSON. But what if you had, say, a nested object in there that was sparse? Okay, it would be very wide. Maybe there are 200 keys that could occur in there, but there's probably only ever 5 of them used. Just take that as an example. It would be super painful to flatten that and have 200 nullable columns. I wouldn't want to, I'd want to be friends, but I wouldn't want to look at your data or use any sort of tooling on that. That would just be bad. So the JSON index is for cases like that. So now you can take that object and say, we're going to bring that in as JSON and build that JSON index. And it can still have more nested objects. It can have arrays. You have, high performance, simple key lookup, chained lookup for nested objects, lookups into arrays, Boolean expressions. I already said arrays, all that kind of stuff. So do stuff with JSON in a performant way. And you do that specifically. The typical use case is that wide, sparse, nested object. So it's there if you need it. Otherwise, what you want to do is you want to flatten the JSON and actually import it if that's the source data. Okay. Timestamp index is just like the range index, except the number is a time. And you get to configure the index in terms of the grain that you want to use. So day, second, minute, year, whatever that, whatever you're rolling up to. You can think of it as taking the timestamp and zeroing out all the stuff below the grain. So if the grain is day, then hour, minute, second, millisecond, just zero all that out and build a range index on what remains. There you go. So there's a geospatial index. I'm just not going to say much about it because this is another one of those things where this is its own talk. Uber, interesting note, after LinkedIn built Pinot, open sourced it, Uber was the first, the other big company to pick it up next. And they were building out Uber Eats at the time. And of course, Uber's whole business is about where things are. And so they had a geospatial library, contributed that to Pinot, built all this stuff. And it's got all the usual suspects in the geospatial world. Distance, contains, point, line, polygon, all that. It breaks the world into hexagons. So if you're a role-playing desktop role-playing game person, this should feel good. Final index. Too many indexes, too much time on these indexes. I gave this talk once, had a friend, he's also a speaker, and he came up to me afterward. He said, that was really good. I think you spent too much time on the indexes. That got a little boring. I'm like, oh, thank you. It's very kind. It's good feedback, though. You need to be able to talk about these things. All right. Now, I work for a company called Startree. Startree was started by the people who created Pinot, and a lot of Pinot committers work at Startree. Our business is a fully managed, cloud-based Pinot service, so you don't have to deploy brokers and servers and controllers and minions. We do it for you. No surprises there. That's not to be confused with the Startree index. Okay, the Startree index was there before Startree. The company was there. This is just an implementation detail that leaked into the interface. It happens to everybody. And the whole idea here is when you've got that, what I described as the bread and butter query, where you're going to filter, group, and aggregate, the Startree index is a way of radically optimizing the performance of those queries by pre-computing them and storing them in the index. So this data, it's funny, there's a lot less ad tech in the Pinot world than you might think. It's not, I mean, ad tech seems like a real-time analytics problem, and it is. Pinot was born and really specializes in user-facing analytics. Okay, so turning OLAP queries into things that power features that you actually use in the app. So users of the mobile app or the website, it's like they turn into decision makers who are getting fed analytics data instead of that just going to dashboards to managers. We're all decision makers now. That's kind of the heart and soul of the Pinot community. It's not really ad tech, but this ad tech example is just easy to understand. And there are some people doing some super cool and not gross ad tech things with Pinot. I always feel like I have to apologize for the example. Look, it's honest work, okay? Now we've got made a video about a year ago with a company based in Colorado who definitely has a name, and I'm blanking on it right now. Sovereign, they're called. It's a US company. And they do like ad placement for sort of like mom and pop recipe bloggers or, mom bloggers or small time, people who want to create content and earn some money on it. They specialize on that. So it's a very nice human story. It's not like tracking your every movement across everything you do. It's trying to help that passionate cook make some money from their recipe blog. It's a great story. Anyway, click data. Look at our dimensions. Country, browser, locale. What's our metric? Ad impressions. The Startree index is appropriate where I am filtering on some number of a few dimensions. I've got 3 here, and let's say I don't know which one of those 3 are going to show up in my where clause on any given query. But I do know I want the sum of impressions. I could also have the average, max, I could have any number of aggregates I want. We're just going to go with sum. What it does is it builds this index, this tree in the index. And if we want to know, say, what were all of the Spanish language impressions for any browser and any country? Well, okay, we've got nodes here. This is the Canada node, the Mexico node, the USA node, the wildcard node. All right, so let's go over here. Country is not in the where clause, so we go to the wildcard node. Browser is not in the where. Oh, I always forget what one I'm doing. It's not Spanish. It's Safari. Okay, so all of the ad impressions for all the Safari users, that's the only term that showed up. So we go country and then Safari, and we found our answer. Or we could say country's not there, browser's not there, but see, Spanish was there. Just got ahead of myself. If only locale equals Spanish was in the where clause, doop, 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 right there. We do that traversal in the tree, and we have our result. Pick it right out. Typically, when people build this index, you know, they're doing benchmarking without it, then they add the index. They think something's broken, something's cached. That's not a real result. That can't be true. You know, it looks like a hack. It's a cool index. For this case, right? It is optimized for a very particular case. If it's Canada, suppose for some reason you're interested in impressions in Canada, Firefox, Canada, any browser, the French locale, you can just find any of these combinations regardless of what is in the where clause. It's pretty cool. You have to use a lot of space for this. You have to create a lot of documents and put them in that index, but it works. All right, I want to talk about ingestion because that gets us to the Kafka integration. And I want to leave a few minutes for questions because that's just polite. So, all right, let's talk about ingestion. Let's say static ingestion of CSV data. Big data here. This is a lot. No way you could do this on your laptop. There's 4 records. It has to fit on the slide. It's just the concept, okay? If you've got petabytes of this, it's going to be fine. We want to get that into a table. That's what we're doing. We're going to get it into a table, into segments. So when we're batch ingesting, we're reading data, parsing it, doing type conversion, creating segments, creating indexes for those segments, and loading them into the cluster so that we've got a table. Now, this is our data, pretty simple. First thing we do is we create a schema file in JSON. Like I said, there's no create table statement. And the nice thing about breaking the schema away from the table config is that if you've got multiple tables with the same schema, well, they can have literally the same schema. You have that one file that you have for all those. So not much to say about the schema. You do have to break out what's a dimension, what's a metric, and what's a date time. You may not have a date time. In some cases, that's okay. In some cases, you need it. Depends on how the ingestion is set up. But those 3 categories, metric, dimension, date time, all of your columns fit into those, and it's kind of there. Now, table config is where a lot of your life is lived. If you're going to get mad at something, it's probably related to table config or the docs on table config. That's a very difficult thing to document in a way that doesn't force you to just go through everything. But anyway, it talks about replication. We didn't talk about tenancy, but that's a thing. We are batch ingesting, etc. There's just a lot to be done there. This is not a tutorial on table config. After that, if you're doing this from the command line, the one command line tool that you run for anything in Pinot is called Pinot admin. Use the add table command, point it to the table config, point it to the schema file. That creates the table. Then, I apologize that there is YAML. You are worthy of better. But there's some YAML. This is a job spec. Remember the minions? This is for the ingestion minion, the static file system ingester. We give it this specification, this command line, again, Pinot admin. Say, okay, go launch the data ingestion job, go read your YAML or whatever it is you want. And then that command line command that I run is going to talk to the controller. It's going to send that spec to the controller. The controller is going to make tasks, send them to minions. The minion now is going to have to be able to see that CSV file if it's ingesting from the file system. Maybe it's an S3. It's going to be able to see that bucket, have credentials on that bucket, wherever it's getting it from. And it actually creates a segment, that segment file itself. And conceptually, okay, this is not literally how it's going to work. Think conceptually, it sends it to the controller. The controller makes a decision about where it's going to go in the server. And as the minion ingests, it keeps doing that. The controller sends those off. Really, what's going to happen there is the minion is going to write that file practically into S3, into a place called the deep store in S3. And it's going to tell the controller, hey, I put this in the deep store at this path. And the controller will say, hey, server 2, there's this file in this bucket, go get it. It's a new segment for you. And that's how that works. Now, real-time ingestion. You got to do batch ingestion before you do real-time ingestion, because real-time ingestion is batch ingestion plus a little bit of magic. Now, there's Kafka, and we're ingesting from Kafka into a table. Pinot is directly consuming from the topic. So there's a server that's consuming from the topic, loading up an in-memory structure called the consuming segment. Now, as soon as a record is consumed, it's put in the consuming segment. The consuming segment participates in queries. So if that server gets a query, right after that record has been consumed, that record is readable. It will affect results in that query. So there is no latency imposed after the consume is complete and it's written to the consuming segment. You don't have to wait or batch them up or anything like that. You're seeing them. But of course, it's a memory, an in-memory data structure. So as it fills up, it then cooperates with the controller, creates a segment, writes that segment to the server. And those segments are just the 1, 2, 3 that you see there. Those are regular old segments on disk. So you consume into this in-memory thing and dump into actual segments. So let's skip ahead a little bit. You kind of get the idea. Here, the controller now, by the way, when I create a table that's ingesting from Kafka, that's called a real-time table in Pinot. A table that's ingesting from batch data is unfortunately called an offline table. Now, that's a little bit of a term of art. Some people, it's a little bit old school, but in analytics, batch data is called offline data. I don't think we really wanted to call tables offline because that really makes it sound like you can't use them, but you can. They're just batch data. Real-time tables are the controller tells the server, picks servers, and it says, hey, here's the Kafka cluster, here's the topic, go consume from that topic. And so to be a real-time table, when you create a real-time table, you're actually configuring the table with bootstrap servers, credentials, topic name, start from the beginning or start from the end, all that Kafka consumer stuff. As soon as you create a real-time table, it begins ingesting from Kafka. So to be a real-time table is that pipe is connected and stuff is coming in. You can create an offline table and never ingest anything into it. It'll just sit there and be a table. A real-time table is active right away. Yeah, so that server is told to connect and is doing those. Let me show you. Here we are. Okay, this is what we need. It's a little more intimate than that. Like I said, this was sort of built down the hall from Kafka, from the folks who were building early Kafka, designed to integrate tightly. If you know Kafka, if you know that ecosystem, you know typically if you're connecting a database either to ingest or to write out, you use Kafka Connect or roll your own, right? Kafka Connect's the standard answer. Never, no, not once in the world of Pinot. The servers themselves are consumers. And in the recommended configuration, they are so-called low-level consumers. So a regular group of consumers, well, or to use the Kafka term, a consumer group, will talk to the cluster and say, hey, Kafka cluster, we 3 group members want to consume all the partitions from the topic called such and such. And the group and the cluster work together to give a fair arrangement, balancing of partitions to consumer group members. And that can rebalance during the life of the group and so forth. It's a cool thing, right? It's a really neat thing. Pinot doesn't do that. You can let it do that, but by default, it's a low-level consumer. So server 1 is saying, I'm not asking which partition. I'm telling you, I consume from partition 0. Server 2 is saying, I consume from partition 1. Server 3, partition 2. If there's replication, well, then there's going to be 2 or 3 of these consuming from partition 0. Right? So it's very connected, very low level. And now each one of those has got their consuming segment that they're filling up, writing segments out to disk. So in a real sense, the stuff in this partition, it's a beautiful thing that we have this kind of log-based world now, and we have microservices that work, and this brand new architectural paradigm for the first time since the 1980s, that is really a different thing for the way people write business software. Logs are great for that, but they kind of suck to read. You can't ask them questions. And so the title of the talk is Making Kafka Queryable with Apache Pinot. There are a lot of different ways that one might want to query a topic. One of those is to get insights about what has happened. That means OLAP, right? To do analytical queries, because I want to know, I want to understand what's been going on in this log. So consuming from Kafka topics in this way is Pinot's way of making them consumable. And it's a piece of infrastructure that you build into your system, right? It's there. And automatically consuming from Kafka. You don't have to do anything more. You can just throw SQL queries at it and get answers. Now, I would love to leave a little bit of time for questions. So I'm just going to put this up here. This is Star Tree Developer, links to videos, podcast, meetups, stuff that you want. Thank you for being here. It's been wonderful.